This problem is on estimating the output ripple voltage in a buck converter. Output ripple voltage is an important parameter in the design of a DC-DC converter. It defines how good a DC output voltage we are getting. This is a buck converter. In a buck converter, the input voltage is 20 volts DC, output voltage is 12 volts DC. The power output is 48 watts and the switching frequency has already been decided. It is 50 kilohertz. We are assuming that the converter is ideal and lossless. The switch is ideal, the diode is ideal, the inductor is ideal, and so on. That means the efficiency of the converter will be 100%, the input power and the output power will be equal. What we are going to do in this problem is consider two designs, one with a large inductor and another with a small inductor. And then compare the output voltage ripple and a couple of other parameters. We are going to see how much capacitor is needed in the case when the inductor is large, and then how much capacitor is needed in the case when the inductor is small. That's a basic idea of this problem. Design 1, this is the large inductor case. L is 120 microhenry. Determine the duty cycle of operation and draw the inductor current waveform. Part B is determine the value of the capacitor C such that the peak-to-peak ripple is 1% of the output voltage. The background material for this part of the problem may be found in two of the earlier videos. One, PE2A2 buck converter, all waveforms in CCM, that is CCM part 2 video. This describes the buck converter operation and also describes how the ripple voltage can be calculated. The second video is PE17 charge balance in capacitors. This goes into detail the charge balance in a capacitor under steady state. You may find these two videos useful in understanding the content of this problem video in greater detail. So let's start with part A. The input frequency is given as 50 kilohertz, so the input period is 1 over 50 kilohertz, that is 20 microseconds. The power is 48 watts, the output voltage is 12 volts DC, so the output current is 48 watts divided by 12 volts, that is 4 amperes. Next, we will determine the boundary current. This is the boundary between CCM and DCM. This has been shown earlier to be V0 Ts by 2L times 1 minus V0 by Vin. Plugging in all the values for V0 Ts, Vin and L, we get 0.4 amperes. If the output current is more than the boundary current, the operation is in continuous conduction mode. If the output current is less than the boundary current, the operation is in discontinuous conduction mode. In this case, 4 amperes is more than 0.4 amperes. IO is more than IOB, so the operation is in CCM. When the operation is in CCM, we know that V0, the output voltage, is dV in. So the duty cycle is 12 by 20, 0.6. Now we are going to plot the IL waveform on this graph. The time axis in microseconds. The total period is 20 microseconds. T on interval is 0.6 times 20, 12 microseconds. T off interval is the remaining 8 microseconds. IL waveform in general is going to look like this. The average of the inductor current or the DC inductor current flows through the load. So the output DC current is the same as the average inductor current, and that is 4 amperes. We can calculate the peak-to-peak ripple current, that is delta IL, V0 Ts by L times 1 minus V0 by Vn. You can notice that the peak-to-peak ripple current under CCM will be twice that of the boundary current. And if you calculate this, it's going to be twice 0.4 amperes. That will be 0.8 amperes. So delta IL, the peak-to-peak inductor current, is 0.8 amperes. We have now marked the delta IL on the waveform. We are dealing with a triangular waveform and the average current is right in the middle of it. I1 is the valley current. I1 is I0 minus delta IL by 2. So that is 3.6 amperes. I0 minus 0.4 amperes. Likewise, I2, the peak current, is I0 plus delta IL by 2. That is 4 amperes plus 0.4 amperes. That is 4.4 amperes. So we can mark these two currents here. So this is the inductor current waveform. Next we will do part B. We have reproduced the inductor current waveform here. Now we will find the value of the capacitor needed from this inductor current waveform. The inductor current consists of a DC component equal to 4 amperes and a ripple component. The DC component cannot go through the capacitor, it goes through the load. The AC component will be filtered by the capacitor, so we can assume all the AC component goes through the capacitor. So the capacitor current will be the same as the ripple current in the inductor. The capacitor current swings from minus 0.4 amperes to plus 0.4 amperes. The wave shape is identical to the ripple current in the inductor. The peak-to-peak capacitor current is the same as the peak-to-peak inductor current, which is 0.8 amperes. Delta V0 is the peak-to-peak output voltage ripple that is equal to delta Vc. The capacitor is directly in parallel to the load, and we are assuming an ideal capacitor without any parasitic series resistance. Delta V0 has been given as 1% of the output voltage. Output voltage is 12 volts. So delta V0 will be 0.12 volts. The charge going into the capacitor in a cycle, Q plus, is shown here. That is the green triangle. The charge going out of the capacitor in a cycle is Q minus. That is the yellow triangle. Under steady state, the charge going into the capacitor should be equal to the charge going out of the capacitor. So under steady state, Q plus plus Q minus should be equal to 0. That is called charge balance. So this waveform shows the capacitor voltage waveform. The average of the capacitor voltage waveform is the DC output voltage, that is V0 equals 12 volts. Now, as the charge is going in, Q plus, the capacitor voltage will keep rising. As the charge is going out, Q minus, voltage will fall and it will come back to the original value. So the capacitor voltage ripple is going to have a waveform as shown. So the peak to peak voltage is the difference between the peak value and the valley value, which is delta V0 is 0.12 volts. And because the voltage waveform is symmetrical, we can expect the valley voltage to be 11.94 volts and the peak voltage to be 12.06 volts, ideally. We need to know the amount of charge going into the capacitor, Q plus or Q minus, both are going to be equal in magnitude. And finding Q plus is fairly straightforward. It is that area, that is half of the base times the height. Base is this interval. Because of symmetry, that interval will be half of the period. Period is 20 microsecond, so that interval is 10 microsecond. And the height, as we know, is 0.4 amperes. If you calculate the charge Q plus, that is 2 microcoulombs. So every cycle, a charge of 2 microcoulombs goes into the capacitor and the same charge goes out of the capacitor every cycle. So delta Vc is the charge by the capacitor, Q plus divided by C. So we need to find C. So C will be Q plus by delta Vc. That is 2 microcoulombs divided by 0.12 volts. That is 16.67 microfarad, approximately 17 microfarad. Usually, because the capacitance tolerance can be quite large, we will be using higher value capacitor. We are assuming here there is no ESR, equivalent series resistance. If the capacitor has a significant ESR, then you have to factor that into account in calculating the ripple. Here we are assuming an ideal capacitor. So this is design 1, L equals 120 microhenry, CCM operation, D is 0.6. The peak of the inductor current is 4.4 amperes and the capacitance to be used ideally is 17 microfarad. Next, we will see design 2. In design 2, we will use a smaller inductor, much smaller inductor in fact. So everything else remains the same. The inductor value is 4.8 microhenry. Now we are going to do the same two problems again. The first one is determine the duty cycle of operation and draw the inductor current waveform. And the second one is determine the value of the capacitor C such that the peak-to-peak ripple voltage is 1% of the output voltage. Two prior videos may be of use to you. One of them is the charge balance in capacitors, which we talked about a bit earlier. And the other one is PE2A6 buck using normalized characteristics. We are going to use normalized equations a little while later, and this video will be useful in understanding how this normalization is done. Now, let's do the first part, the duty cycle of operation and the inductor current waveform. There's a bit of overlap between this part and some part of the video PE2A-P3, which goes through a problem on DCM operation. The overlap is there in order to make each problem appear complete in itself. The period is 20 microseconds, 1 over 50 kilohertz, and the output current 48 watts by 12 volts output voltage. That will be I naught equal to 4 amperes. First, we need to find out whether the operation is still in continuous conduction mode or it has moved to discontinuous conduction mode or DCM. The boundary current IOB is V naught Ts by 2L times 1 minus V naught by Vin. Everything else remains the same. The only thing that has varied is the inductance L. Instead of 120 microhenry, we are using 4.8 microhenry. So the boundary current is going to go up. I naught B, when you substitute all the values, is 10 amperes. In the previous case, I naught B was 0.4 amperes, whereas now it is 10 amperes. I naught, the output current 4 amperes, is now less than the boundary current. 4 amperes is less than 10 amperes. So the operation is in DCM. For the DCM, we will use the output voltage formula or the equation using base V naught normalization. In base V naught normalization, the normalizing voltage factor Vn equals the output voltage equals 12 volts. In, the normalizing factor for current, is V naught Ts by 2L. Plugging in all the values, we get that as 25 amperes. The normalized input voltage Vn, N stands for the normalized variable. Vn equals Vin by Vn. So 20 by 12 volts, 1.6667. ION, the normalized output current, is IO by IN, which is 4 amperes divided by 25 amperes. That will be 0.16. The equation for duty cycle with base V naught normalization is given by square root of ION divided by Vn times Vn minus 1. This equation has been derived in the video PE2A6. Substituting the values for ION and Vn, we get D as 0.3795. So you can notice that the duty cycle is lower to get the same output voltage 12 volts in the case of DCM as you would expect. Let me note the duty cycle here. D is equal to 0.3795. Now we will plot the inductor current waveform. This shows the wave shape of the inductor current. During this interval, the current starts from 0 and reaches some peak value. And then when the switch is switched off, the inductor current freewheels through the diode. The energy in the inductor is not sufficient to maintain the current throughout the off interval, and the current falls to 0 before the start of the next cycle. And once the current falls to 0, the current stays at 0. Neither the diode nor the switch conducts. So in this mode of operation, you notice that there are three intervals of operation. On interval when the switch is on, and the off interval when the switch is off is split into two sub-intervals. One when the diode is conducting, that is the freewheeling interval, and the other when the diode is also off, that is the discontinuous conduction interval. Now we need to find the values of the peak current and also the time intervals. First, let's find the value of the peak current. The T-on interval is D times Ts, that is 7.59 microsecond. T-off interval is 20 minus 7.59, that is 12.41 microsecond. The peak inductor current is V in minus V naught by L times T on. V in minus V naught by L is the slope of the inductor current during the T on interval, and T on is the duration of the on interval. Evaluating this, we get IP is 12.65 amperes. Next, we will do TF and TD calculations. TF is the freewheeling interval and TD is the discontinuous interval. TF will be the peak current divided by V naught by L. V naught by L is the magnitude of the slope of the inductor current during the freewheel interval. IP by that will give you the freewheel interval. So substituting the values, we get 5.06 microsecond. TD interval is the remainder of the T off interval. So TD will be T off minus TF, that is 12.41 minus 5.06, that is 7.35 microsecond. So this is the inductor current waveform. Suggested additional work, homework if you will. First is show that the average inductor current IL average equals the load current I0, 4 amperes. An additional homework is show that the average input power, that is the DC power, equals the output power, that is V0 I0. Next, we'll determine the capacitor value such that the peak-to-peak ripple voltage is 1% of the output voltage. This is the current waveform. The average inductor current is the output current 4 amperes. Since the peak-to-peak ripple voltage is only 1%, all the ripple current will flow through the capacitor. So if you take IL and then subtract 4 amperes from it, we will get IC, the capacitor current. The peak current is 12.65 amperes minus 4 amperes, 8.65 amperes, and the valley current is 0 minus 4 amperes, that is minus 4 amperes. The green area here represents the charge going into the capacitor Q plus, and the trapezoidal yellow area here represents the charge going out of the capacitor Q minus. Q plus plus Q minus equals 0 by charge balance. We have to find the Q plus charge divided by the capacitor to find the ripple voltage, or take the Q plus divided by the ripple voltage to get the capacitor value. So in order to find the charge Q plus, we need to find the area of this triangle, that is half TB times the height of the triangle, which is 8.65 amperes. Notice that in this case, this time TB is not equal to this because it's not a symmetrical waveform. So we need to calculate the TB value. And how do we find TB? I have taken the T on interval and divided it into T1 and T2. Likewise, I have taken the freewheeling interval and have divided it into T3 and T4. TB, as you can see, is T2 plus T3. So we need to find T2 and T3. We can use simple geometry to find the value of T2. Let me mark some points here. A, B, C, D, E, F, G, and H. Triangle ACB and triangle ECD are similar triangles. Because of that, the ratios of the sides will be equal. So AC by CE will be equal to AB by DE. AB, the magnitude is 4 amperes. DE is 8.65 amperes. And AC is T1, CE is T2. So T1 by T2 is 4 by 8.65. T1 plus T2 is the on interval 7.59 microsecond. So T1 is 7.59 minus T2. So 7.59 minus T2 divided by T2 is 4 by 8.65. Solving for T2, we get 5.19 microsecond. We can find T3 in a similar way. Triangle FHG and triangle FED are similar. So FH divided by FE will be HG divided by DE. So T4 by T3 is 4 by 8.65. And T3 plus T4 is the freewheeling interval 5.06 microsecond. So that means 5.06 minus T3 by T3 equals 4 by 8.65. We can solve for T3 and we get 3.06 microsecond. Substituting the values for T2 and T3, Q plus can be calculated. T2 plus T3 is 8.25 microsecond. Now Q plus will be half times 8.65 times 8.25 microsecond. So the charge going in every cycle is 35.68 microcoulombs. Much more than the 2 microcoulomb which we saw earlier. So C is Q plus divided by delta Vc. Delta Vc is the same 0.12 volts, that is 1% of 12 volts. Q plus is much larger, so C will be much larger. If you do this calculation, 297.3 microfarad, nearly 300 microfarad. Design 2, to summarize, L is 4.8 microhenry, it is DCM operation, the duty cycle is 0.3795, IL peak is 12.65 amperes and the capacitor value is 300 microfarad. Compare that with design 1. Design 1, L is 120 microhenry, CCM operation, D is 0.6, IL peak is 4.4 amperes, C is 17 microfarad. The inductance value in design 1 is much larger, while the capacitance is lower. In design 2, it is the other way. The inductance value is smaller, but the capacitance is much larger. Generally, for the same energy storage, capacitors tend to be more compact. Inductances tend to occupy more space, so a larger inductance means a bigger converter. You pay a price in terms of the size of the converter. Look at the peak current. Here the peak current, inductor peak current is higher in DCM design. That means the switch peak current, the diode peak current will be higher. All the components of the converter, the inductor, the switch, the diode have to be rated to withstand this higher current. So the circuit RMS currents will be higher, the device RMS currents will be higher, device peak currents will be higher. In general, the losses in the converter will be higher in the DCM design. You can see the significant difference in the peak current. The output current is 4 amperes. In CCM design, the peak value of the inductor current is not much more than that. So the inductor current it's nearly constant with a small ripple on it. Whereas here in DCM design, the current is quite peaky. So you can expect design 2 to be less efficient than design 1. Another difference we have not covered in this example, the dynamics of the converter will tend to be better in a DCM operation compared to CCM operation. But in the case of buck converter, even the CCM operation, the dynamics is not too bad. So in general, people prefer the CCM operation design rather than DCM operation design in the case of a buck converter, mainly because of the higher currents and higher power loss in the DCM design. That's the end of this problem video. If you like this video and this series of videos, please subscribe to this channel and click the like button. Thank you.